Let's do a probability problem. Let's say that we have an unfair 8-sided die. It is twice as likely to roll a prime number, 1 included, than not a prime number. Let's answer the following questions. So question 1, give the probability of rolling 3. Well, actually, before we jump into the questions, right, I need to know how the dice is unfair. I need to find the probability of a 1, 2, 3, 4, or 5, 6, 7, 8. Right. So if I have that probability space, omega, I know the size of omega is equal to 1. All right. And a prime number is twice as likely. So let's say there's a 1, 2, 3, 4, 5, 6, 7, 8. Those are my 8 different options. Now let's find all the primes, including 1, 2, 3, skip 4, 5, skip 6, 7, and not 8. All right. So the prime numbers are supposed to take up twice as much space as all the other numbers. So however much area that takes up, and that takes up, and that takes up, and that takes up, and this takes up. This is supposed to take up only one of those. This is supposed to take up only one of those. And this 8 is supposed to only take up one of those. All right, so what do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So a prime number is going to take up 2 of those 13ths. So a 1 occurs with a probability of 2/13. A 2 occurs with a probability of 2/13. So does a 3, because those are all prime numbers. They take up 2 spaces. And a 4 is not prime, so that's only going to take up 1 of the 13ths. 5 is prime. 6 is not prime. 7 is prime. 8 is not prime. Now, when you add all these up, you should get 1. You should get your entire sample space. Okay, and this satisfies, as everybody can see, the probability of rolling a prime number is 2 times the probability of rolling a not prime number. So this is what we have. This is the picture. This is how the dice rolls. Now let's start answering questions. Give the probability of rolling a 3. Well, that's just me going to my table and saying, well, what's the probability of rolling a 3? So the probability of a 3 is 2/13. All right, number 2, give the probability of rolling an even number or a 1. So the probability of being even or 1. So while we solve these, we're going to solve them first with an equation, and then we're going to go back to our table and just intuitively talk about why the equation makes sense. So probability of even or a 1. So I could be even, or I could be a 1, right? Either of these things could happen, and it would satisfy this definition of being even or 1. And now I need to think, is there any overlap between evenness and 1s? Or do I need to subtract off any intersection? So the probability of being even, that's a 2, a 4, a 6, or an 8. If I add those probabilities up, I get 1, 2, 3, 4, 5. So there's 5/13 of my space that satisfy being even. The probability of a 1 is just 2/13. Now, is there any overlap between even and 1s? No, right? 1 is not an even number. So you don't really subtract anything. When we add these, actually, let me bring it up here. When we add these, I get 7/13. All right, number 3. Let's see. Give the probability of rolling an even number or a prime number. So by the same equation, I could be even, or I could be prime. And then I don't want to double count the even and prime numbers, so I need to subtract off the intersection. So there's 5/13 probability of being even. I add to that the probability of being prime. That's 2, 3, 4, 5, 6, 7, 8, 9, 10. But notice, so let's go through this. Probability of being even. That was a 2, a 4, a 6, or an 8. And then the probability of being prime. That was a 1, a 2, a 3, a 5, a 7. So notice we counted something twice. Right? We counted that 2/3 twice. So I need to subtract off the intersection, the probability of being even and prime, and that is exactly the probability of being a 2, right? Because that's the only even and prime number. So I need to subtract off the probability of a 2. So 5 plus 10 minus 2 gives me 13. Out of 13, that gives me a 1. And notice that makes sense because look at our table. Every single event is counted, right? Every single event that's possible either satisfied being even or being a prime number. So of course we were going to get a probability of 1. All right. Number 4. What does this say? Give the probability of rolling an even and a prime number. So the probability of being even and prime. So by the equation, this is going to be the probability of being even times the probability of being prime given that you were even, right? Because you're even and you're prime. So what's the odds of you being even? And then if you're even, what are the odds of you being prime? Right, I need both of these things to happen. So the probability of being even was 5/13. And what's the probability of being prime given that you're even? So if we go back up to our table and I just look at the even numbers, there's only one of those that's prime, right? That 2/13. So out of all the even numbers, how much space does the even numbers take up? 2, 3, 4, 5. Oh yeah, of course 5. So out of the 5/13 space that the even numbers take up, how much is taken up by a prime number, which is the 2/13. Right, and if you simplify this, you get 2/5. So the probability of being even and a prime number is the probability of being even times the probability of being prime, given that you're even. And this returns what? The 5's cancel, and we're left with 2/13. Okay, let's go to the table and talk about why that made sense. The probability of being even and prime, you could think, well, there's only one number that satisfies that, right? The 2. And what's the probability of a 2? It's 2/13, right? So the equation checks out. We are on to number 5. Give the probability of not rolling an even number. So the probability of even complement. So by the equation, we could say that this is 1 minus the probability of being even. Probability of even was 5/13. What does this give us? 13 minus 5, that's 8/13. Right? Or if we go back up to the table and just think about it for a minute, what's the probability of not being even? Well, it's being an odd number. So 1, 3, 5, or 7. So that's 1, 2, 3, 4, 5, 6, 7, 8, right? 8/13 of my space. All right, last one. Number 6. Give the probability of rolling a 2 given that we rolled a prime number. So the probability of a 2 given that we know we drew a prime. So this equation is just a rearrangement of the multiplication equation, right? What are the chances that we rolled a 2? Oops, there we go. Probability of prime, right? What are the odds that we rolled a 2 if we know that it's prime? Well, if we know that it's prime, then we don't have to compare to the entire sample space omega, just compare to the size of prime, because we know that we drew a prime number. And then how big does the space 2 take up out of the space of prime numbers? So if we do this, the probability of a 2 was 2/13. The probability of a prime number, I think we've done that somewhere. 10/13. Oh, I copied that down wrong. This should be the probability of a 2 given that you're prime. Or the probability of 2 and prime. How much space does the 2 take up out of a prime? So the probability of 2 and prime, well, that's just this 2/13. And the probability of prime was 10/13. So if we simplify this, we get 2/10 or 1/5. So the probability of 2, given that you're prime, is 1/5. And if we go back up to the table and just think about that for a minute, if you know that you're prime, then isolate yourselves to the 1, the 2, 3, 5, and 7. How much space does that take up? 2, 4, 6, 8, 10. Right, out of the 10/13, how much does a 2 take up? Because that's the only even number. Oh, not even. We were looking at a 2 specifically. So how much space does a 2 take up out of that? 2/13. Right, so intuitively, you get in fact, not only the same answer, but the same equation.